So, hey everyone, I'm Rob. I lead engineering for Neural Magic. Been with the company for about 2 years, and as Michael kind of mentioned, I'm very actively involved in the vLLM community, and I'm a committer on the upstream project. And so today, I think a lot of everyone in the vLLM community has heard a lot about the v0.60 release, where the headline is we delivered a really large speed up on H100 GPUs for Llama 8B and also for Llama 7DB. So really large speed ups across the board. And today I just wanted to discuss how we did this. It's really been a great collaboration across the vLLM ecosystem. Lots of companies, UC Berkeley, Neural Magic, Anyscale, IBM, Databricks, working together to address some of the performance overheads that we had in vLLM prior to v0.6.0. So in terms of agenda, I wanted to cover a couple topics. First is just the fundamentals of LLM inference, why it's a hard problem, what challenges arise in building an LLM inference server. Then I'll describe vLLM's internal architecture for how we support a key optimization called continuous batching. Diagnose some of the performance issues, prior to v0.6.0 as a result of this overall architecture. The key optimizations we made over a couple of months to resolve some of this. And then I'll discuss some of the outstanding projects that we have ahead of us to continue driving performance relative to where we are today. This won't go into anything about GPU execution itself. The performance gains have come completely from reducing the overhead and the scheduler side of vLLM. So if you're interested at all in learning about how we make GPU execution go really fast, take a look back at the presentation Tyler did last week on Cutlass. But that's a separate topic, so we won't cover that today. So to get started, just with the real fundamentals of LLM inference. An LLM fundamentally is a function that predicts the next token in a sequence. So if you think about it, basically we're computing the probability of the next token, the nth token, given the previous series x0 through xn-1. And this is what an LLM model does, is it takes that input and then gives you a probability distribution over, the nth token. And so when we think about generating text with an LLM model, effectively what's happening under the hood is that these calls are chained together in passes through the model, which takes a prompt and then sequentially generates one token at a time. So the folks at Anyscale had a really nice blog in the past, which helps to visualize this on the right-hand side. And basically what we see is that, for an input that's length 3, we use those first 3 tokens to generate the 4th token. And then given those first 4 tokens, we use that to generate the 5th token, and so on and so on and so on. And so fundamentally, what's happening under the hood is we're chaining together these calls one after the other through the model. And, generating 1,000 tokens requires 1,000 passes through the model. And so the consequences of this are that a single generation can last for multiple seconds, right? Like if you're generating 1,000 tokens, this will take multiple seconds to occur. And I think anyone that's interacted with an LLM can feel this in terms of how long it takes to generate the text. And so a key challenge that we face in building an LLM inference server is how do we handle those multiple concurrent requests that are coming in when each one can take up a long amount of time. And so historically, looking at computer vision and natural language processing models, inference servers used a technique called dynamic batching to batch up requests and send them through the model. For traditional models like BERT or YOLO in the computer vision space, this worked really well because each inference request only required one pass through the model. So the way that these systems would work is you would set up a little queue, wait for n requests to come in, pass those off to the model, execute, get all the results back very quickly. This worked really well, but is a bad strategy for LLM inference. This is effectively batching at the request level. And you can see on the left-hand side how this sort of looks inside of an LLM. If you think about it, if you get 4 requests, if one of those requests 1,000 tokens, you would have to wait until, and the other 3 only requested 1 additional token, you would have to wait until that really long request is done before new requests come into the batch. And additionally, let's say you have an inference request that lasts 3 seconds and a new request comes in the middle of that, we can't add that to the batch until everything is done. And so this request level batching that you saw from traditional inference servers is a really, really bad strategy that will underutilize the GPU and create large amounts of latency for end user use cases. And so continuous batching, which is the optimal technique for running LLM inference, takes a much, much different strategy, where rather than batching requests together at the request level, instead we batch together at the iteration level. And so a simple diagram on the right-hand side shows what this sort of looks like. Let's say we had 4 slots in your LLM server. When request 1 finishes, it gets through the first 6 tokens, we can evict that request from the batch and add a new request in. And so this allows us to have new requests entering the system as other requests are being generated, reducing the latency, increasing the GPU utilization, and fundamentally improving all of the metrics, between latency and throughput that the LLM server is able to do. But what you can see is this is a much more complicated problem for an LLM inference server. You have a much finer grained level at which you're batching, and you need to be a lot more careful about scheduling, about communicating with the back to the inference server, dealing with memory management, et cetera, et cetera. It's a much more complicated challenge, and fundamentally, vLLM's internal architecture is set up in such a way to make continuous batching happen efficiently. And paged attention, which is sort of the original innovation that kicked off all of this amazing community around vLLM, is a really key optimization that's important when you're dealing with continuous batching. And so to get a little bit into the weeds, how does vLLM do this? How does vLLM manage this continuous batching structure internally to achieve the high throughput and low latency in handling requests? vLLM is architected with a class called the LLM engine, which is responsible for doing this continuous batching. And you can think of the LLM engine operating internally inside of vLLM, running in a loop constantly, with really 3 steps to that loop. First, scheduling. Next, executing. And 3, processing outputs. The scheduler is responsible for determining what work to do. Have certain requests been completed? Do we have new requests coming in? It allocates new memory to these requests to deal with the KV caches, and it fundamentally decides what work should be done at that individual batching step. The model executor is responsible for taking the work that is scheduled and passing it off to the GPU workers. As Michael kind of talked about, inside of vLLM, we natively support tensor parallelism, sharding the model across multiple GPUs. There's a complex layer inside of vLLM that takes the inputs, prepares them, and then broadcasts them to each one of those workers. Again, this is happening on the CPU. And lastly, once the model does execute, we have to process the outputs, doing things like streaming them back to the API server, or detokenizing and checking for stop sequences, evicting items from the batch that are complete. Again, all of this is sort of happening on the CPU and keeping track of all of this metadata and scheduler state that's needed to enable this fine-grained batching that gives us the throughput that we want. And so all of this is a simplified picture of vLLM. There's a lot more complexity under the hood, but there's really only this one part of vLLM that's actually executing the models. And most of the code at the higher levels of the system is dealing with managing this memory and ultimately passing things off such that we can do this autoregressive generation in a really tight way to enable continuous batching. The next piece I just wanted to talk about is to understand how the different components of vLLM perform as the amount of load on the system grows. So one really important thing to understand is that H100s are really, really, really fast. There's a constant on GPUs that sort of determine the performance of the generation step of an LLM. And this is the memory bandwidth of the system. The memory bandwidth is a parameter of the GPU that determines how fast you can move the weights from the GPU RAM into the on-chip memory. For a decoding phase of LLMs, the computation is bound by this parameter. So on an H100, we have 3.35 terabytes per second of memory bandwidth. A 16 gigabyte model, an 8 billion parameter model, is about 16 gigabytes, which means that we can move, the weights from RAM into the GPU on-chip memory at a rate of about 5 milliseconds. So internally inside of vLLM, you should understand that the GPU is operating really, really, really fast and, is basically getting about 5 milliseconds per iteration, 5 to 7 milliseconds per iteration. And as load increases on the GPU and we move from batch 1 to batch 256, because we're in this memory-bound case, the latency of doing a batch 16 or batch 64 decode is actually very, very, very close to the latency of doing a batch 1 decode. I have a chart here on the right, but what you can see is at batch size 1, because we're so memory bandwidth bound, we get about 0.8 seconds of latency to decode 100 tokens, versus at batch 64, we're getting less than a second to sort of do that. And so you can see that as the load increases on the GPU, we actually see basically the same overall amount of GPU execution time. But the rest of the system, the scheduling, the input preparation, the output processing, this all happens on the CPU and basically grows approximately linearly with batch size. You have to do N scheduling operations and output processing operations. And worst of all of this runs inside of a single process in Python, and the GIL inside of Python, the global interpreter lock, prevents sort of any concurrency. So this is not great in terms of the setup for, the amount of throughput that we can get. And this is the actual chart that we all looked at as a team on the vLLM community that Johan made, which covers how much time is actually being spent in each step. And so you can see, for 48 seconds of running vLLM, 25 of those seconds was being spent in actual model execution, but significant amounts of time were being spent in that prepare, input, and broadcast phase. Significant amount of time was being spent in the schedule phase, and a significant amount of time was being spent in that process output phase. And when you add in the API server on top of this, which is another sort of 30% overhead, we were getting basically only 30% of the time, 38% of the time being spent in GPU operations. So clearly what we needed to focus on is how can we increase the performance of the CPU parts of vLLM to make it faster. And so we kicked off 3 large projects to enable this. The first was a really deep collaboration between Neural Magic and IBM, which worked to bring more concurrency into vLLM by separating the API server and the LLM engine into 2 separate processes. Inside of Python, there's a concept called the GIL, which is the global interpreter lock. Basically, Python, even if you're running with multiple threads or multiple async IO tasks, from the perspective of the programmer, those can work concurrently. But inside of Python, only one of those can execute on the CPU at a time because of this concept called the GIL. And so what we were seeing is that under high load, the API server layer of vLLM was contending for CPU resources with the core LLM engine inner loop that I talked about on the prior page. And so what we did is we split these off into 2 separate processes and introduced a package called ZeroMQ as the messaging protocol within vLLM. We sampled lots of different protocols. We started looking at gRPC. We looked at a couple of other ones, even using raw sockets. But we decided that ZeroMQ provided a lot of really, really great performance and a really good user interface for us as developers to use to create this message passing protocol that didn't rely on any locks or anything at the Python layer. We're going to be introducing ZeroMQ into other parts of vLLM, into more of the core inner loop, because we had such a good experience using this. And I think in general, this is a really good pattern for building, actual concurrent Python programs. But anyways, using this overall technique, we were able to increase the throughput by 25%. And we have an additional optimization that I'll talk about later, which resolves all of the overhead associated with the API server. The next optimization that we looked at was something called async output processing. CUDA is fundamentally an asynchronous operation on the GPU relative to the host code. And so inside of, when you launch a CUDA kernel, the host code can continue executing while the GPU is running. And so effectively, what we did is introduce offsets into the core vLLM engine that enabled the output processing to happen at the same time as the GPU is running the forward passes, as opposed to these happening synchronously. Effectively, we had to offset the work by one step such that these didn't have a data dependency, but this resulted in about a 7.5 throughput gain from enabling asynchronicity inside of vLLM. And the last optimization that made a really, really big difference is to just reduce the overall amount of CPU work that we're doing. In particular, a key optimization that Anyscale implemented is something called multi-step scheduling, where rather than scheduling and allocating memory at each step of the inner loop of vLLM, we schedule the next n steps such that we can only run the CPU work 1/n times. And this had a very, very significant impact because it reduced the overall times we had to prepare input and reduced the overall number of calls to the scheduler function, and resulted in about a 70% throughput gain as compared to the same model running in single-step mode. So in summary, this has eliminated most of the overhead on the CPU side of vLLM. For Llama 3AB, which is effectively the most challenging case because the GPU runs fastest, this resulted in a 2.7x overall speed up between vLLM v0.5.3 and vLLM v0.6.0. For Llama 7DB, the GPU execution takes a lot longer, so the overhead is not as painful, but we still achieved almost 2x throughput gain in between the two releases. And so this has been really awesome, and it was a really great collaboration across the vLLM community with Neural Magic, IBM, Databricks, Anyscale, and Berkeley really working together to achieve these results in a relatively short amount of time. In terms of looking forward, we're continuing to optimize some of these. We're continuing to push on some of the techniques that I sort of talked about. One technique that we've been working on, Neural Magic and IBM have been working on together, is to bring 0MQ closer into the core loop of vLLM. Right now, the async LLM engine uses async IO internally to manage concurrency, which is challenging because the core inner loop of vLLM is running inside of the async IO event loop. This turns out has significant overhead in the task switching that occurs. And so we have been working to enable more concurrency inside of the LLM engine by bringing 0MQ into that inner loop and enabling concurrency through a message passing protocol as compared to the async IO, task switching. And you can see this has, again, significantly more throughput gain, 33 items per second as compared to the 23 items per second I quoted before. And so this is something that actually has landed and will be in the next release. One of the key negatives of our initial version of multi-step scheduling is that, and this was one of the pieces of negative feedback that we got as part of the v0.6.0 release, is that the inter-token latency of the multi-step scheduling was quite a bit worse. So because we were scheduling 8 steps at a time, we were only generating new tokens 1 out of every 8 steps. And so you can see the inter-token latency, which is how long it would take between new tokens being generated, was up at about 150 milliseconds. And so one of the optimizations that was really easy to do inside of this new MQ-LLM engine class is enabling, asynchronous streaming. So as the tokens are generated, we send them out 1 at a time back to the users. And the MQ-LLM engine and this PyZMQ library made it really easy for us to do this. And you can see that for basically no impact on time per output token, we're able to reduce the inter-token latency down quite a bit. And lastly, we've been working on filling out the overall number of optimizations that multi-step works with. So one of the limitations in v0.6.0 is that multi-step doesn't work with chunk prefill. Chunk prefill, as Michael mentioned, is another optimization which helps to smooth out the inter-token latency inside of vLLM by overlapping prefill and decode compute into the same batch. You can see an example here is, let's say you have a prompt of length, 8,000. We split that up into chunks of 2,000 and then overlap those with decode operations inside of vLLM. And so what chunk prefill enables you to accomplish is to smooth out that time per output token by preventing these long pauses to process new prefills and bring them into the batch. So you can see with chunk prefill enabled, we have a draft PR in place. This enables a significant reduction in the time per output token that we're able to achieve. And so this, we're hoping will be in v0.6.2. We have some active work, but again, continuing to push on the performance. And so that sort of covers it. The main message is v0.6.0 of vLLM has a significant improvement in H100 performance, primarily due to the reduction of CPU overhead. As we look forward, we're continuing to push on these overall ideas. In particular, we want to migrate our architecture to have a fully asynchronous scheduling, such that this can be completely overlapped with the GPU execution and reduce as much as possible the overall CPU execution time. Additionally, as we look towards the future, the GPUs are just going to get faster and faster and faster. And so this type of optimization is something that will become increasingly more important and will be an increasing focus of the team over time. And just thank you to everyone in Neural Magic who worked on this project, Alex, Varun, Andy, and also to a huge collaboration across various organizations, Anyscale, IBM, Berkeley, Databricks, who contributed to this overall effort. So I'll pause. I know that was a lot. Hopefully it's a helpful summary of how LLMs work, how vLLM works, how do these things impact performance, and then ultimately what we've done. But yeah, happy to answer any questions about all that.
Yeah, there's definitely some questions in the chat if you want to take them on.
Could you list some of them off to me?
Yeah, so definitely, there's a question on kind of came out with like what isn't compatible with multi-step, and do we have like a public tracking doc? I'm not actually sure if we have a tracking doc, but certainly like chunk prefill, as you went over, is a major one. I know speculative decode. If you have some other ones at top of mind.
Yeah, sure. So I would describe multi-step in v0.6.0 as being in beta state in terms of the overall production readiness of the system. Some examples of things that are not supported yet are things like n greater than 1 sampling, where you're having multiple generations for a single prompt. Things like beam search that are kind of more in the gut, that require changes to the guts of vLLM. Chunk prefill is the most obvious one right now. I think some of the logits processing can be a little bit finicky so far. So some of the guided decoding features are definitely something we're working on hardening. There is a tracking issue for these things, and we've just been burning them down over time. So it's been really helpful to get the community's feedback so that we can address these. And ultimately, we plan to turn this on by default as soon as we feel like it's hardened enough for real production use case. But at this point, things are starting to stabilize quite a bit, especially with this v0.6.1 release. Definitely things are in a lot better of a shape. But there's really no, there is a bit of a trade-off in terms of like turning on multi-step. Like one of the main things is it will increase likely your time to first token. If you think about it, we're scheduling 8 steps at a time. If a new request comes in the middle of those 8 steps, that can't be added to the batch immediately. I still think it's like clearly the right trade-off to make for most cases because it, obviously just increases the overall throughput that you get by so much that the impact to time to first token is definitely worth it, in my opinion. But obviously it will depend on your workload. The other thing I would say is the reason we're moving towards this fully asynchronous scheduling architecture is that, ideally we'll be able to reduce the number of steps that have to be scheduled at once down to 2 or 3 or hopefully even 1, 8 is kind of the value that we've centered on right now as the default parameter that we would sort of suggest. But ultimately where we want to go is make more of this asynchronous, overlap it with the GPU even more, and then prevent this trade-off on TTFT from existing. Sorry, I kind of got off topic from the original question, but yeah, that's kind of my overall thoughts on multi-step in terms of the hardening of the feature for production use.
Oh yeah, I think that's good to run through here. Another one that I think was directly about your presentation was how many clients were set to make the performance breakdown on page 13?
Sure. So this page 13 is this one?
Yes.
Okay. Yeah, so this use case looks at the LLM engine. So this is not running in server mode. This is running in offline batch mode. So basically, we took shared GPT, which is a set of prompts. We ran 1,000 prompts through the system, and we just profiled, where is time being spent. So this is effectively maxing out the, overhead in vLLM. Like this is the maximum number of requests that you're ever going to have. Like an offline batch use case will always be running at whatever the max batch size that you set is. By default in vLLM, we set that to 256. So this is as much overhead as you could possibly have inside of the LLM engine. I talked about, in addition, when we profiled that same workload running through the API server added an additional 30% overhead relative to the chart that I have here. Unfortunately, because of async IO, it's not so easy to make a nice chart like this that explains where the time is being spent when we're working in the API server, because that's just, the profile or output is just much more complicated when you're looking at async IO. But this just shows an offline batch use case. So it's effectively maxing out the number of active requests inside of vLLM.
Yeah, great. I think another one there was the scheduler, model executor, and output processors are all part of the engine. So I'm wondering if splitting the API server into a separate process from the engine can make the system faster.
Yes. So this is what this overall project was about, was splitting the API server into a separate process. And, this enabled, when you split them into separate processes, now each one of those processes has a separate GIL. So they can run on separate CPU cores at the same time and effectively have no overhead other than the synchronization associated with the message passing from 0MQ. But what we found is 0MQ works really, really, really well as a concurrency management system inside of vLLM. Like, I really, really enjoyed how this sort of works. It enables you to have totally lock-free synchronization across your different processes. It's a really, really good way to think about doing concurrent programming where the threads are executing and they're sending messages to each other, blocking on those messages. This works really, really well. It prevents you from having to do things like having locks in Python, which makes the interfaces really clean and makes the performance really good, because all of this concurrency is handled down in the ZMQ level at these, inside of really optimized and hardened C code, right? So yeah, that's what the goal of this project was to pull this off. And where we want to go over time, and with some of the asynchronous scheduling that I was sort of talking about as the next phase of work in terms of the scheduler, we're going to be bringing more of that into the deeper levels of the engine. So running the scheduler in one process, running the actual model executor in a separate process, and then using 0MQ to pass messages between those. That's kind of the architecture that we're sort of planning. And this will enable the scheduling to happen in a separate process as the GPU execution, and these could be fully overlapped with each other. And ultimately, we hope, push CPU overhead to epsilon. So I think this worked really well for the, for the API server. The MQLM engine is kind of the next step in terms of this, in bringing the 0MQ stuff closer into the LM engine. And then the async scheduler that we're sort of planning as the next phase of optimization brings this technique even closer into the core of the system.
Yeah, I think that's pretty good. There's definitely a lot of questions coming in. I think, yeah, Sanjay, really appreciated your specific answers there.
There's one other thing that someone questioned about, like, what's the API server written in? So One thing that is really great about vLLM is that we offer multiple interfaces. So Michael kind of talked about up front that we have the offline batch, we have the API server, which are both great interfaces. Like lots of people use these in production directly, and run their inference services using these directly. But another really nice feature of vLLM is that these APIs, this LLM engine, this async LLM engine, and then ultimately this MQLM engine that we've been working on are also something that a lot of companies take and use directly in their inferencing system. So for instance, let's say you run Triton server from NVIDIA. There's a really clean way to integrate Triton as the front end with the async LLM engine, or ideally MQLM engine as the overall backend. And so this is definitely something that you can explore if you need more customization of the front end, and definitely something that Neural Magic is happy to work with you on if you do need to customize the front end. But as you kind of can see, there takes some care to get this right. And so, but that's definitely something that can be explored over time. And also, one of the nice things about ZeroMQ is that it is language agnostic. So, we currently use ICP for the communication protocols. This can be swapped out for TCP. And so you can actually have, whatever protocol that you want to sort of talk to those sockets. So yeah, that's one of the nice things about vLLM is that this internal system is pluggable, and we do plan to keep these interfaces robust.
Okay. I think there's still a few questions coming in. Some of these are related to questions that were asked ahead of time. I think some of the things we could maybe cover is like, what would be the like optimal parameters for deploying like Llama 3.17 dB on vLLM. I think like this is definitely, specific to what your workload and what your hardware is. How many GPUs do you have to do types of parallelism on? Are you on A100s, H100s, A10s? Definitely open to have more of a back and forth conversation on that, Derek, if you're willing to. Yeah, there's a question on the performance update blog post. Why do we only benchmark on 500 prompts? Don't we face the long tail issue, low batch size at the end for the infinite QPS offline scenario? I'm not sure exactly long tail and offline, I think that definitely matters, but like in like a true offline scenario, you're not spending that much time in the tail. You're spending the majority of the time crunching through the large amounts of, batch size that you have through your offline prompt. We see this a lot through doing like model evaluations, right? Where you need to evaluate over 2,000, 4,000, 100, 10,000 like different prompts. There's a little bit of time waiting at the end for maybe the last few, but for the majority of the time, you're stuck in the chunk. Regarding that specific blog post, right? The point there was to really show like serving workloads, and that's why there were like 3 different types of workloads with like shared GPT, a decode focused workload, and a more pre-fill focused workload.
One thing that I would say is Roger, who's on the call here from Roblox, has implemented a really nice benchmarking framework that's integrated into vLLM inside of our GitHub. So there's like a benchmarks repository, and we have a few different modes that can be benchmarked. So we have benchmark throughput that looks at, the LLM class and does offline workloads. We have benchmark serving. Benchmark serving has a couple of different data sets that it can load. Shared GPT is just one that we've kind of standardized on and push against because it looks a lot like what we see from actual production use case. There's also another data set in there that's called Sonnet. Sonnet allows you to generate, to determine the number of prompts and number of decode tokens as much, to set it to whatever you want, right? And so this allows you to have some more flexibility in terms of determining what the input shapes are that you have in your system and, profile your overall workload. like as I kind of like talked a little bit about like in some of the fundamentals of LM inference serving, you can see that like the shape of your workload in terms of like the number of input tokens versus the number of output tokens and the QPS rate has really big impacts on how long each request is going to take and how much time is being spent in the prefill phase versus the decode phase. And so what I would suggest is there's not really a one size fits all in terms of like, this is the best configuration for all workloads, or this is the exact amount of GPUs that you need to serve Llama 8B. Like that will depend on what your input shape looks like, what your query per second looks like, all these different types of things. And so I would encourage that anytime you're moving into a production setting or trying to determine how much hardware resources that you need, that you start from the fundamentals of what does my workload shape look like? You use some of these serving scripts to assess, okay, if my workload looks roughly like this, I can get this many QPS on my system. From there, you can start tuning arguments such as like, what is my chunked prefill size and how does that impact my workload? You know, how much tensor parallelism should I use? Should I use 2 copies with TP4 or 1 copy with TP8? You know, you can start looking at how quantization impacts things. Like FP8 is useful in some cases. FP4 is maybe more useful for low QPS workloads. But really, that's the overall, strategy that I think anyone should use as they're trying to think about what ARGs to do is to start with your workload shape, start with that data, and start tuning arguments from there to push forward and determine the fundamental structure of the infrastructure. And so I think we can do a better job as a vLLM community in terms of helping users understand what are the different flags and when should they be used and what people should try. And maybe we can do another section on that in the future if that's of interest. But yeah, that's kind of what I would say is there's not a one size fits all, and you should really always start with data and these benchmark strips as the way to kind of come up with the answer of what the config should look like.
Okay, there's a few more questions in the chat. If you want to answer them sort of offline as we're going, I'll go through the rest of the presentation, but we'll definitely sync back up on the questions that were asked offline. Just want to make sure we get to address them all.
Sure.
I just wanted to update and cover real quick basically what's new in the major release and the 2 hotfix, or rather minor release and the 2 hotfixes we've had since then. So as noted before, added support for a lot of multimodal models, including Pixtral, Lava Next, Video, Qwen and Qwen2-VL. Also, like good progress on supporting multi-input, so like multiple pictures for Lava and Intern VL2 models. And I think just yesterday there was Qwen2.5 launched, and there's no changes needed for that. And including with the tool calling, which was really cool to see, as mentioned before. In terms of performance enhancements, there were support and optimization for AWQ support. Basically, these are new kernels written in Triton that aren't exactly useful for NVIDIA GPUs, but they did add support for AWQ for AMD GPUs, actually. And you can see some performance improvement with them. And obviously, memory improvements through using AWQ, which is a weight-only quantization method on AMD GPUs. There was also some additional, progress on multi-LoRa, so you can dynamically load and unload LoRa adapters from the API server, so making it easier to deploy multi-LoRa on your models as a service. There's additional work on, batch runner and getting like progress reports on that. And then we did add support for NVIDIA ModelOpt FP8 checkpoints, although that's pretty early. We are working with NVIDIA on trying to support their quantization formats that they use for TensorRT LLM. And then, there was also an update to the Docker image for Python 3.12. This hopefully doesn't break anyone's deployments, but we saw there's some performance improvements kind of towards what Rob was talking about in terms of, the CPU being bottlenecked in a lot of the Python CPU code, host code. So 3.12 helps a little bit with this, particularly on underpowered CPUs. And we hope to, follow Python along as the performance of the language server gets better. Yeah, and then in the bug fixes, most of these were related to Pixtral, as we released very quickly. Well, actually, the first hotfix was for supporting Pixtral as it was released, and then we've had several bug fixes and improvements for multi-step scheduling and tool use, as these have been major sort of community features, performance features, and we're continuing to work on multi-step bugs or features, so the inference metrics. Like inner token latency get better, like Rob was talking about with the streaming. Yeah, and that's basically all to cover here. So now we can cover on some of the questions that were asked ahead of time. So we sort of worked through and try to put some links in here. So definitely go through the slides if these are your questions or you're interested in the answers. Yeah, there should be some links here. So for the best commercial license, open source models at the moment for Japanese, I don't think there's many like Japanese specific trained models, but certainly the Qwen series of models from Alibaba is trained on a variety of Asian languages and claims to be pretty good at Japanese. And they just released Qwen2.5 with various model sizes from single digit to multi-digit billion parameters. And most of the models are Apache 2.0, so that should be good for you. Yeah, there's a question on plan to support Medusa heads for speculative decoding, Medusa version 2, and top K for tree styles of speculative decoding. So Medusa is already supported. Medusa 2, I'm not personally sure what that is exactly, but there is an RFC and a few issues open on Medusa or speculative decoding in general. So definitely put your questions in there and requests in there, and the people working on speculative decoding will definitely see it. Yeah, on K-serve model mesh support, Rob, you wanted to talk about this?
Yeah, I mean, I think like as it relates to higher level Kubernetes orchestration systems and custom resources that K-serve implements, this has not really shipped as part of vLLM. We kind of shipped the serving runtime, we shipped the Docker image with vLLM, we shipped the binary, the PyPy wheels with, that you can install. And ultimately, we leave it up to whatever orchestration systems that we want to fit into. In terms of K-serve, I'm not personally familiar with model mesh. However, I know that K-serve implements K-serve has a concept of a serving runtime, which is an inference engine, basically implementation. And I think as of v0.11 or maybe v0.10 of K-serve, vLLM is a kind of native serving runtime inside of it. And additionally, in v0.13 of K-serve was released the OpenAI protocol. And so I think that the K-serve community has been working very hard to make vLLM run well inside of K-serve. And but we don't really have any plans as the vLLM team to ship K-serve or any other Kubernetes orchestration alongside our overall package. We would leave that up to the kind of K-serve community or any other orchestration communities that wanted to make vLLM a first-class citizen inside of their systems. So yeah, that's what I would say.
Okay. Makes sense. So yeah, there's a question on like new feature request or developing new features, how to maintain state per request for a draft worker.
Yeah, I can expand on that question if it's helpful, or I can, I guess, punt until the next office hours.
Sure. Yeah. Go ahead.
Yeah. So basically, I'm starting from kind of the ngram speculative decoding implementation, which is currently in the repository, and it uses this execute model request class to encapsulate all the information related to what it's providing speculations for. And for what I'm working on, basically having auxiliary information like RAG or some other user-generated speculation attached to each request and this requires adding some state to the model. So I'm just wondering, kind of in that context, like, is that something that I can, utilize and extend and, write information to from the context of these speculative decoding workers, or are these workers essentially memoryless? I don't understand all of the kind of multi-processing things going on and how to synchronize all these things across workers. So just want to make sure I'm not like, going down a very, very complicated path for that.
Yeah. I think like searching through some of the previously or like implemented backends for speculative decoding or other workers, I found this one PR that claims to keep track of like sequence IDs that were assigned bonus tokens in previous forward passes. And it mentions like needing to know when a request is being dropped or finished. So I would say that. And then there's also like an n-gram, like an n-gram speculative decoding pass or speculative decoding worker that obviously needs to know like what were tokens that are in like the prompts previously with like a long context. And I assume it has maybe a different data structure for accessing that efficiently and searching that. So definitely, looking at the other workers would be great. But also if you want to open an issue on this, we have like a specific internal channel for speculative decoding. And that would be a good place to maybe like introduce you to the group and see if like maybe the people that work directly on that would want to like talk to you more in depth.
Sounds good. Thanks.
Sure. Another question here on how to effectively manage fine-tune LLMs. Not easy when you want to start different applications with different LLMs. So, it's really difficult with full fine-tuned models. It's much easier if you have LoRa, adapters that you can hot swap on or possibly like batch like per request. We support this in vLLM through the multi-LoRa support. So, certainly the much more cost-effective way to serve various fine-tune LLMs with limited resources is to move away from full fine-tuning and try to achieve the same result with LoRa adapters, even if you need to go to larger rank LoRa adapters. Really, LoRa is adapter. That and using the multi-LoRa support would be the best way to efficiently use the same base model but with different fine-tuned wrappers. I think, we're already on the second page. Nice. So the last question here is, are there any recommended deployment arguments when optimizing for time to first token versus optimizing for throughput? Certainly. I think the big one in terms of time to first token is to not use chunked prefill, because chunked prefill is something that's goal is to improve time per output token or inter-token latency, so that we're always trying to do, decode batches. But and then we just try and fit in as much of the prefill tokens as we can into the current decode batch. If you don't have chunk prefill enabled, then generally if there's space in the KV cache to hold the request, we're going to schedule that prefill as soon as possible. So you should get that time to first token for that request, scheduled as soon as possible. And there you're just looking for, what is the maximum amount of flops I can get on this GPU for this model. And they're obviously both for time to first token in the aspect of prefill time and total throughput time, assuming you have large batches of requests to decode. You're going to want to look at activation quantization that makes sense for your GPU. So that means like int 8, W8, A8 for Turing and Ampere GPUs, and FP8, WA, A8 activation quantization for, Ada Lovelace and Hopper GPUs.
They're a good parameter that is also, I think, especially useful, like if you're looking at, maximum seeks. So like inside of vLLM, there's effectively an internal parameter that determines the number of requests that get batched together. And 256 is a really good place for serving workloads. But for offline batch, I think you can typically squeeze out another, 15% or so by increasing that, especially if you're running like an 8B parameter model on like an H100 where you have a lot of KV cache space. You can often crank that up quite a bit higher and achieve even more utilization. So that's another parameter to experiment with.
Yeah, great. Definitely feel, I mean, really, thanks for all the questions. This has been a great number of questions. So if there's none other, or you want to talk more one-on-one, feel free to hang on after, but we'll close this out for now. So sort of at the end here, we want to say definitely contribute to vLLM. We have, some issues marked with good first issue, but really, look for RFCs, look for issues, look for pull requests. Feel free to comment, emote, do whatever you want to show your support of what people are working on or what you wish they would work on. Our best way to understand that is, the people that want to use the features and will use them once they're implemented. And of course, use vLLM to build things, to, develop your own growth of what you need inference serving for. Please give us feedback on the office hours. We're welcome and open to doing other formats of this, but this has been working well, so we appreciate you coming here. And come meet us at upcoming events. We'll be at the Race Summit with the vLLM track that's going to be there. Many vLLM committers. I think most of the core vLLM team is going to be there in San Francisco. And in NeurIPS, Neural Magic will certainly be there. And I'm sure many of the other companies and contributors are going to be there in Vancouver. So, and aside from that, please, follow the vLLM Twitter page to see what events and meetups are happening over the next weeks and months. And then lastly, Neural Magic is hiring. If you're looking to work on vLLM or working in open source inference serving, we're always looking for talented engineers to join us on that mission. So thanks very much for coming along, and another great office hours. Really appreciate all the questions and feedback today. Let us know how we can be better help to you. And talk to you on the Discord, talk to you on the GitHub, and thanks for being a part of the community.